no challenge at all.
We'll do here is we'll look at mobile telecom basics. So we'll look at some of the basic principles, some of the terms, some of the concepts, and then an overview of the industry. The next thing we'll look at after that, next we'll get into the identities. There's many identities that are used in mobile telecommunications more than just your phone number. As a matter of fact, inside the network, your phone number is not really used too much. It's used to set up a call to you, but inside the network to page you, to bill you, to find you, to register you, all that, there's different identities. There was what was known as a first generation, a second, third, fourth, and currently that line is the fifth generation. But it's not like buying an automobile where you kind of get rid of the old one and have a new one. These generations coexist, and there's a lot of interworking between them. And then with each generation, there's different signaling protocols, and the protocols are really, like it says, really the lifeblood of the communication. What's necessary for your mobile to be mobile? What's necessary if you're in your home network? What's necessary if you roam some? So again, that's what we'll take a look at in the next couple of weeks. Today, we'll just take a look at some of the wireless and cellular concepts. It is it's a kind of an amazing device that not too long ago was just used for communication. Not too long ago, you were tethered to your home or to a wired telephone. And today, not only is it mobile, but it's very reliable today. A much longer battery life. If you had a mobile phone back in the 80s or 90s, the battery life was not very long at all. Performance today is unmatched. Unbelievable graphics and picture taking, high quality camera, very high speeds and getting faster all the time. Good high fidelity sound. So again, just it really is for a small device, quite an amazing device. So when you look at this, how does it work? Most people might see a antenna occasionally. Some of them you might see a kiosk where they're selling mobile phones, but beyond that, there's a lot that goes on in the entire mobile telecom industry. So how does it work? How does it know where you are? How does it know if you go to another network? How does it know what you subscribe to? How does it know if you have any restrictions? Maybe you're restricted from mobile terminated calls, or maybe some kind of restriction on short messages. Well, how does the visit system, how does that information go between these networks? And how does it know when you're roaming in another network? How does that billing get back and forth? Do when you go to another network, is that free or are you charged for that? Certainly you don't get multiple bills at the end of the month. So there has to be some kind of agreement between these networks. So those are the kind of things that we'll explore. These are the four pioneers when it comes to wireless. The first one was back in the 1800s, James Clerk Maxwell, and he mathematically theorized that electromagnetic waves exist. Heinrich Hertz, he demonstrated, he's the first to demonstrate that there were electromagnetic waves. The first one to do a practical demonstration, that was Marconi. And way back in December 1901, he sent the letter S between Cornwall, England, and Newfoundland up in Canada. There's still some dispute today whether he really sent that or whether it was really heard, because the letter S in Morse code is just dot dot dot. So some thinks he probably just heard static, but nonetheless he does get credit for proving that electromagnetic waves could travel. The other pioneer, and this goes back to the 1930s, 1940s, was Edwin Armstrong. He developed frequency modulation. He pretty much went broke in his lifetime because he was fighting companies that were AM or amplitude modulated, particularly RCA. But he ended up dying rather young. But again, he is credited with developing frequency modulation. So these are the kind of the four pioneers. When you look at wireless communication, take a look at the spectrum here. The entire spectrum from the radio, then through infrared, visible light, and all the way up through here, cosmic rays, which these are 10 to the 25th power hertz, just incredibly narrow waves. If you look at the radio wave, raise the hand. Is there a question? Really, Tesla was more with electricity. Yeah, Tesla was more with electricity. Tesla and was more that was more on the electrical current side. But he could probably include Tesla in here also. I mean, he did some work along these lines. But this was, I just wanted to show that EM waves were theorized, they were demonstrated, they were proven, and then improved on. Those are kind of the four. That's a good point. Yeah, I could probably include Tesla, give him a slide also. Good point. Good point. Absolutely. Sure. When you look at the wireless, the radio spectrum, the lowest band here is the radio band, and these the frequency. Frequency is just the number of cycles, and they're measured in what's known as hertz. And so these cycles go up in ever increasing narrower cycles. So the lowest one is 3 hertz, which this is the extra low frequency. These kind of frequencies down here are good for things like submarines or maritime, where the radio actually follow the curvature of the Earth. The higher you go up in frequency, the more radio takes on the characteristics of light. In other words, it becomes more focused. You can see up here, even and that's at the high end of the radio spectrum. Kind of the ideal radio frequency exists right here in what's known as the ultra high frequency band. And that's roughly 300 megahertz up to 3,000 megahertz. And so most of your radio, your mobile telecommunications, TV, microwave, Bluetooth, two-way radios is all in this frequency band. This becomes very, very ideal. So today, cellular mobile telephony is in that band. Now, there's advantages to going higher. You can go in a higher frequency into here, the extra high frequency, the super high frequency. However, radio waves, the higher the frequency, the more they die down much quicker. It's kind of like light. It'll only go so far and then it dies down. Whereas the lower frequencies have more power. They have more power. They can go through buildings. They can go through windows. They can go through walls and everything. Whereas the higher frequencies is more like the characteristics of light. So you can do radio communications up in here, cellular telephone. However, you'd need a lot more antennas, antennas, because again, the radio waves do not travel as far. Likewise, can you go down? Well, again, this might be okay, but you need very large antennas. It'd be not practical. So really the kind of the lower end is somewhere in here and the higher end is somewhere in here. So most of it exists, if not all of it exists here. With 5G, though, there is some frequency up here. This is ideal if you have a lot of radio antennas. This is ideal for very high speed data. But today, almost everything exists somewhere around 400 to 500 megahertz up to about 2,000 megahertz, somewhere in that frequency range. That's called the ultra high frequency range. Some of the, and that's just a change of direction when a radio wave bounces off of an object. So, which is a good thing. Otherwise, you'd have to, radio waves could never, you have to have always line of sight. So here, radio waves do bounce off of different objects. So that's a good thing. It's called reflection. Higher frequencies are much more sensitive to reflection. The lower frequencies just kind of push their way through more. Higher frequencies will bounce off of objects. Attenuation, that's the loss of your signal strength as it travels through a medium. Again, higher frequencies experience much more attenuation. The higher the frequency, the more, once a radio wave leaves an antenna, the more it just dies down much quicker. Refraction. Reflection was the change of direction when a radio wave bounces off an object. Refraction is the change of direction when it passes from one medium to another. You know, the best example is that is a straw or a pencil, let's say, in a glass of water. When you look at it, it appears that it's bent. Well, that's just a change in the waves passing one medium to another. Frequencies are more sensitive to refraction. In other words, they refract less. The higher the frequency, the more it takes on a beam. Propagation is just their behavior. And wavelength, this is an important one. Wavelength is by the sign, the Greek letter lambda, and the wavelength is the velocity of light, which is 300,000 megabits per second. So that's the speed. So it goes, meters per second. So you go 300 million meters per second. That's the speed of the of light, and you divide that by the frequency in hertz. So if you have something down here, if you have something in the, let's say, the 900 megahertz, that's 900 million hertz. So it's really 300 million divided by 900 million. Roughly, the wavelength for cellular is roughly 300 million divided by 900 million, roughly 1/3 of a meter. So the way, think of the wavelength going like this, it's roughly 1/3 of a meter, roughly that far. That's 900 megahertz. Now, the higher the frequency, the more that is together. This wavelength, it's the number of crests that pass any one point in 1 second. So again, that's just the wavelength, just to give an idea of the. You think of a wave going across some kind of medium. Yeah, please, a question. Yes, the frequency you go here, the better the better the signal can penetrate and work around objects. So the better it is at the lower frequency. However, you can't go too low because you need giant antennas. So there is a practical limitation. The higher the frequency, the more clear it is, the higher the data rate. However, you get more dead spots because it forms more of a beam. It doesn't go through things as well. So in general, the higher the frequency, and a lot of the cellular communication works at 17, 18, 1900 megahertz, kind of in this range. That's a little more susceptible to objects and to dead zones, whereas the lower band in here, roughly 7, 8, 900 megahertz, kind of in this range right here, is much better for pushing through. So, in general, that's the case. In general, the higher the frequency is clearer, it is higher, faster data, but it's much more susceptible to objects. It's much more susceptible to um, even the higher the frequency. If you get up in this band here, higher frequency is even susceptible to raindrops, because again, it blocks it. It takes on more of the characteristics of light. Yeah, good point. Good point. Okay, excellent. So the early mobile telephony was basically just a two-way radio. And what that means is that there was only a limited number of channels that you could talk on. And what these operators would do, and this goes back to the 1930s, 1940s, even into the, they would place an antenna at a strategically high location. So, and you had, let's say, several channels. Well, you could use those channels. Well, once those channels were done, once everyone's using those channels, no one else could get in. They were blocked. You only had 4 or 5 channels. And it takes 2 channels to talk, unless it's like a walkie-talkie. A walkie-talkie is one way. I talk to you, hello, Raphael, how are you doing? Over. And then he would talk to me. Well, we're sharing a channel. But when you have duplex communication, it takes 2 channels, one for me to talk to you, one for you to talk to me. You've probably seen old, maybe old movies, had old car phones, and they had to call an operator in order to call someone on the landline. So this was, there's only a few channels here with an antenna that was kind of, just think of an antenna strategically placed on a high mound or on a high building somewhere, and only a few data channels for these customers to use. Once the channels were occupied, you were blocked. And you always needed operator assistance to connect to the landline. So what happens how do you increase that capacity? There's only 3 ways that you're going to increase the capacity. Number one, you can go get more frequency, more channels, but it takes a certain amount of frequency to talk. So if it might take, the channels are this wide as far as frequency bands, they're like 20, 30 kilohertz wide. So you have a channel, and that's what you use for voice. So you either have to have more customers. That's one way to do it. Another way to do it would be to improve this air interface, improve how you modulate the signal. So if you make improvements on here, you can get more capacity. But there's a third way that's the most efficient way to gain more, to emit frequency, less power, put less power out here and reuse that same frequency at some distance away. That's the concept of cellular. With cellular, instead of having a tower that's just blasting out frequency, you reduce the power of that frequency and you reuse those same frequencies at another distance away, a non-adjacent distance away. And that's the whole concept of cellular. So this is the need to increase capacity. You either have to go get more frequency, and that's not the easiest thing in the world to get. When you look at this right here, everyone wants this frequency band. You've got everyone's here, and you can't just grab that frequency. Most, if not all countries, you have to go to the government. Like in the United States, the Federal Communications Commission. You have to go to them and get a license. You need a license to operate in certain frequency bands. And there's no there's no unused frequency, especially in that range. So that's kind of unlikely to get more frequency. Another way is you improve the air interface, how you modulate the signal. And there's different ways. We'll talk about some of the different ways that you can improve the air interface. The other thing is if you, you can't have a very cell a few meters wide and expect it to work if you're driving down a motorway at 80 kilometers or something like that. So there's a that's the key to cellular. The key to cellular is to reuse frequencies. So you use low powered transceivers in these small areas, and these small areas are called cells. And they're drawn as hexadecimal cells. Radio waves don't follow, cell, but that's conveniently how they're drawn. They're drawn as these six-sided cells here, as these hexadecimal cells. So anyway, that's kind of the concept of cellular is this whole part here. So that's the real capacity breakthrough. The real capacity breakthrough was cellular communication. And early on, these have changed now over time, but early on, the most efficient use of this, it was what's known as a 7-cell reuse pattern. So you could have, if you had some number of channels, let's just say you had 300 channels. I'm just making that number up. There's a few more than that. But let's say you had 300 of these 30 kilohertz channels, but you want to make them duplex. So you only have 150 channels, because if 300 is, these are channels, but you want to be able to talk duplex, not just like a walkie-talkie. And you need some channels for control, some for voice, but some for control. So if you roughly divide those 300 channels into 1/7, let's say, of each one of these. So you put 1/7 here in cell number 1, 1/7 here, 1/7 there, wherever number 2 or 2 is here, then 3, 4, 5, 6, and 7. Whatever those are, you can reuse those at another non-adjacent cell. So whatever frequencies you have in 5, you can reuse over here, because you don't emit a lot of power. The power here is not so powerful that you would blast it and hear it over here. And that's the whole concept of cellular. The whole concept of cellular is to reuse frequencies. And one of the most common ways is this 7-cell reuse pattern. There's concepts also with this, and the concept being, what are the cells themselves? How often do you reuse frequency, and how much can you reuse it? How do you hand over from one cell to another, and then from one cell to another, and cell to another? Because let's say this here to here, a different frequency, here to here, a different frequency. And that's for you stay within the same system. That's intra-system handover. But how about if you're on a cell here that's controlled by this switch, but now you go this way and you're controlled, you're in a cell that a different switch. That's an inter-system handover. So those are the two, or basically the 4 concepts of cellular. The cells themselves, how big are they? I mean, are they very small? Well, again, that's going to depend. If you're in a stadium and people are walking, you can have very small cells. If you're on a motorway going between cities, towns, and people are driving, you need larger cells, because again, it's got to know when you're handing off from cell to cell as you're using your phone. If you're in an area where there's maybe housing or something like that, you can have little larger cells. If you're in a walking area, small cells. So there's different types of cells and different types of reuse patterns. I think my time is up today, so we will leave it here. And any questions?
Hello.
Yeah, yeah, I didn't hear
Yes.
anything there. Is that Jeff?
I wanted to find out why you mentioned that the towers had to be non-adjacent. Is it because the waves interfere with each other, or is there like a particular reason to why they have to be non-adjacent?
That's a good point. Yeah, why not adjacent? Because if this, let's say this cell tower is emitting frequency, and this with this tower here is emitting a frequency here, well, you can't reuse those frequencies on an adjacent cell because it would bleed over. So people that are assigned a radio frequency here, you would interfere with someone on that same frequency here. So these cells have to be non-adjacent. And the most common way is this, and if you divide up, and it's not always divided up evenly, 1/7, 1/7, 1/7. It's not always like that. But if again, just if you visualize that, the frequencies you use here, you can reuse them up here again, but it can't be adjacent because if it was adjacent, one one here would interfere with the same frequencies there because you have to have a unique frequency when you're talking on cellular.
All
Now,
right.
things change as time goes on. There's different modulation schemes, and we'll talk about those. From just a point of view of visualizing, it'd be like if you and I had a walkie-talkie, and we choose channel 3 on the walkie-talkie, and someone's right next to us using channel 3. It's not going to work. We would hear each other. I would talk, and everyone would hear it. So you
Yeah.
have to use different frequencies.
Okay.
Okay, does that make sense?
Yes.
Excellent. Well, then we will take a look. I guess, Ralph, you want to take over here? Okay. Yeah. In other words, these antennas. If you think of these antennas as kind of like being in the center of the cell, but that's not how they do that. They put them so they're sectorized. In other words, this one cell like here would use 120 degrees here, 20 degrees here, and 120 degrees here. I mean that's how they're sectorized. Was that the question, or is there a different question besides that? Yeah. So these, and you'll see these cell. If you look and see these antennas, you see that there's like three of them around here. Each one is beaming 120 degrees out. That's very common because it'd be very efficient to have center and use all 360 degrees. That's not an efficient way to do it. Now, one other thing is these cells are drawn like this as hexadecimal, six-sided figures, but we know radio waves don't follow that. Radio waves don't, they don't stop at the border. So a frequency here will bleed for a little here and so on. But anyway, this is just a convenient way to share. But that's the real kind of the breakthrough concept is cellular. And the idea of cellular has been around since the late 1940s. However, However, the the switching equipment required to do all of this really didn't come about until the 1970s. So quite a while for the others. Hello, yes. Okay. Well, I could, but we can do it Monday. We can pick it up Monday. You know, you've got your class to teach too, so we can pick that up on Monday. Yes. Oh, you need the no, yeah, Monday we'll go into a little more detail, and then I've got we've got some questions. We're going to have a little bit of interaction on Monday when we get a little bit further into this. But in the meantime, if you have any questions, you can send me an email, and I will answer them, and we'll pick it up here on Monday at the same time. Okay, and everyone, and enjoy your weekend. It's November already tomorrow, so wow, it's time is marching on. But yep, that'll work. We'll certainly we'll do that. Yep, absolutely. Yeah, we don't want you don't want to make it just a lecture part. We want to be able to communicate and maybe. And in the meantime, this weekend, see if you can spot some cell towers out there, and see if you can just say, yeah, those things are probably at 800 megahertz, sending frequencies out. Okay, just kind of look for them. Okay. Ah, okay. Sounds good. Yes, that would be wonderful. Please introduce. I would like to get to learn it one. In fact, I'll write it down.
Hello. So who is starting? Can I start?
This is Abdul.
Okay. Thank you, Mr. Ralph. So my name is Dennis Kofi Aholu. When you think about money, think about me.
Okay, so Abdul, I think. Hello,
Hello. Yep. Yep.
Abdul, I think that's it. Oh, yeah. When you think about this, you guys
Okay.
a lot.
Okay.
Yeah.
My name is Ano.
And if you think about thoughts, think about me.
That's Philip. Okay.
So his name is JJ Lilia.
Uh, my name is Jefferson Ampudi, and I like to watch Formula One.
Thank you. Yes.
My, my name is Nene.
Okay.
When you think about food, I'm your guy.
Okay, my name is Sahid Ambal. When you think about me, think of adventures.
Hey, Raphael, you almost forgot me. Raphael, you almost forgot me. I'm with you in spirit. Okay, so my name is David.
Hmm.
If you think about me, think about construction.
Construction. Okay. Okay.
Hi, my name is my name is Jude. Yeah, I enjoy car racing, and then I'm a huge fan of the stock market.
We hear you, Jude. Jude
Fan of
JS.
who now? Okay, Jude. Welcome.
Thank you.
Yep. Let me know what time on Monday. That sounds good. All right, everyone. Okay. Well, very good. Enjoy your week. weekend, everyone. And we'll see you the same time, unless Raphael gives me a new time. We'll see you on Monday, and we'll continue with talking about cellular communications.